Okay, so last time we started talking about heat exchangers, and specifically we talked about how if you want to get a solution for any specific configuration, you have to do differential energy balances on the two fluids, and then you get some coupled set of ordinary differential equations that have to be solved, and then you'll get ultimately a solution that when you couple with the energy balances and knowledge of the UA should be enough to actually solve your heat exchanger problem, right? So we did this exercise for the specific example shown here, which is a counterflow heat exchanger, and we got this additional equation, which when coupled with these two equations is enough to give you a solution. And there is an equation like this that you could derive for every configuration. Some are relatively simple, like this one. Some are much more complicated because they involve the solution of partial differential equations. But ultimately, these three equations, 1, 2, 3 together, constitute the solution, right? So this is the solution in what is probably not the most convenient form. If you tried to solve the quiz for the last lecture, you hopefully were able to do it, but you probably found out that it's not that easy to actually solve these three equations and three unknowns. You have to have good guess values. You have to make sure everything converges, and so that's what has motivated people to put these into the form of an effectiveness NTU solution, right? And that's the form that people typically would go to in order to actually obtain solutions for heat exchangers, right? So you wouldn't probably have these three equations. Instead, you would have an effectiveness NTU solution. So let's talk about that today. So how do I get rid of this? So the first thing we have to do is define the terms effectiveness, NTU, and capacitance ratio, because all an effectiveness NTU solution is an expression of our solution in terms of a relationship between three dimensionless variables. And the three dimensionless variables are the effectiveness, the number of transfer units, and the capacitance ratio, right? So if I take these three equations and do algebra, I can put them into a form which is just an algebraic relationship between effectiveness, NTU, and capacitance ratio for a counterflow heat exchanger, right? If I had a different equation here for a parallel flow heat exchanger, I'd get a different relationship, but it would still be a relationship between effectiveness, NTU, and capacitance ratio, and that's what an effectiveness NTU solution is, right? So it's some kind of a relationship between these dimensionless parameters. I think the first thing we need to do then, I guess obviously, is understand what the definition of these parameters are. So let's start with, before we do that, let's just sort of fast forward so that you see what I'm talking about. If you go to a table where there's functions and these that do this as well, for heat exchanger solutions, what you're going to see are tables that look like this, right? So if I look at this table here on the left, you'll see that there is a solution. Let me find my pointer. There's a solution over here for every different kind of configuration that we talked about, right? Counterflow, parallel flow, cross flow with every permutation of mixed and unmixed, and shell and tube with different numbers of shell passes and tube passes. And over here, every one of these is expressed as a relationship between effectiveness, NTU, and capacitance ratio. That relationship is different for every one of these configurations, but that's what we're trying to understand today is, how did these relationships come to be? And actually, if we take the equations that we derived and do enough algebra, we ought to be able to derive this relationship here. Or over here, same relationship, just expressed as NTU equals some function of effectiveness and capacitance ratio, versus over here, effectiveness is some function of NTU and capacitance ratio. And we'll talk about why one is more convenient than the other for some problems. So we're going to take this equation, and this equation. So let's go forward here. So, this equation, this equation, and this equation, and we're going to express them in terms of effectiveness, NTU, and capacitance ratio. So first of all, let's talk about what effectiveness is defined as. So effectiveness is sort of your efficiency, right? It is the performance. It's the rate at which the heat exchanger is transferring energy, so Q dot from the hot fluid to the cold fluid, divided by the maximum possible rate that it could be transferring energy, right? So it's Q dot over Q dot max. It's a number that has to be between 0 and 1, right? 0 being your heat exchanger is doing nothing, 100% being your heat exchanger is doing the best it could possibly do, right? So where does this Q dot max come from, right? Usually, if you remember from thermo or really anything, you know, the trickiness of understanding an efficiency definition is understanding this limiting behavior, right? So what is Q dot max here? What is the best it could do? And the way you think about Q dot max for a heat exchanger is you go to the energy balances on the two fluids. So here's an energy balance on the cold fluid. It says that Q dot occurs because you're going to heat the cold fluid up from TC in to TC out, right? So the best that I could ever do is I could heat the cold fluid up higher and higher and higher, but the hottest I can ever get it is TH in, right? If I look at the cold fluid comes in at TC in, I'm adding energy to it, so I'm heating it up. What's the hottest I could ever get that cold fluid? Well, the hottest I could ever get that cold fluid is I could bring it all the way up to the hot fluid inlet temperature. I can't get it any hotter than that because that's the hottest temperature in this entire heat exchanger. So from the standpoint of the cold fluid, Q dot max is the capacitance rate of the cold fluid times TH in minus TC in, right? TH in being what I would plug in here as the hottest I could ever get that cold fluid. So I could do the same thing, but now thinking about it from the standpoint of the hot fluid, right? The hot fluid energy balance says Q dot is C dot H times TH in minus TH out. So again, as I make my heat exchanger better and better, I'm going to cool that hot fluid down more and more. So what's the coldest I could ever get the hot fluid? I'm coming here at TH in, I'm cooling it down. The coldest I can ever get that hot fluid is the cold fluid inlet temperature, TC in, right? That is the coldest point in this entire heat exchanger. I'll never get the hot fluid colder than that. So Q dot max from the hot fluid's perspective is C dot H times TH in minus the coldest I can ever get the hot fluid is TC in. So I have two different estimates for the maximum possible heat transfer rate. And of course, it's the smallest of these two that actually governs or controls the performance. So Q dot max, the Q dot max that I use in the effectiveness, is the minimum of this Q dot max from the cold fluid side and this Q dot max from the hot fluid side, right? So it's the minimum of these two quantities. If you look at this, they both have TH in minus TC in, they're just different capacitance rates. So this Q dot max is actually just the minimum of these two capacitance rates times TH in minus TC in. So it's C dot min times TH in minus TC in. If you want to think about it, you get Q dot max by taking the fluid flow that has the smallest capacitance rate and changing its temperature the most that you possibly can, right? That's the best your heat exchanger is ever going to do is you take the fluid that has the smallest capacitance rate and you either heat it all the way up as hot as it can get or you cool it all the way down as cold as it can get. You can't do any better than that. So if I plug this equation into the effectiveness here, I get that the effectiveness is Q dot divided by C dot min times TH in minus TC in, where C dot min is the minimum of the two capacitance rates. So that's our definition of effectiveness. Our definition of the number of transfer units, NTU, is just a dimensionless conductance, UA, and I make that dimensionless by dividing by C dot min. So this is basically something like the dimensionless size of the heat exchanger, right? I can make my heat exchanger bigger by either increasing UA, right? That is making it physically bigger, or alternatively, I can keep the same size heat exchanger, but I can decrease the flow rate that I put through it. So that makes it look bigger as well, right? That makes it bigger in terms of the job that it has to do. So that's what NTU is. And then finally, capacitance ratio is C dot min over C dot max. So capacitance ratio is a number that has to be between 0 and 1, right? So effectiveness has to be between 0 and 1. NTU can be any number greater than 0, right? It can be 0 to some huge number. Capacitance ratio has to be between 0 and 1. The capacitance ratio is really telling you how balanced the heat exchanger is, right? So a balanced heat exchanger is one where the capacitance rates of the two sides of the two fluids are about the same. And what that means then is that the two fluids, as they flow through the heat exchanger, they'll change temperature by about the same amount, right? That's a balanced heat exchanger. An unbalanced heat exchanger is one where one flow has a much bigger capacitance ratio than the other fluid. And that what's going to happen physically in that situation is one of your fluids is going to change temperatures a lot. The other one is hardly going to change temperatures at all, right? So a classic example of an unbalanced heat exchanger is a heat exchanger where maybe you're doing some kind of a phase change, right? So like an evaporator. On the refrigerant side, the refrigerant, if it's pure fluid that's evaporating at constant pressure, its temperature isn't changing at all, right? So it has an effective capacitance rate of infinity, whereas on the other side, you might have a single-phase fluid, and its temperature would change some, right? So it has a finite capacitance rate. Well, that's a capacitance ratio of 0, right? It's some finite value over infinity. That's going to be 0. Anyway, these are the definition of those three-dimensionless parameters. So what we have to do then is take whatever solution we're interested in getting an effectiveness NTU solution for. So we're going to do this for the counterflow heat exchanger, right? So we have two energy balances which are the same regardless of configuration, but then this equation at the bottom is very specific to the counterflow heat exchanger. We're going to take these three equations and try to do algebra to put them into the form of a relationship between effectiveness, NTU, and capacitance ratio. And it truly just is algebra, right? So we'll go through the steps for this one, but the point being that you understand that it's really just algebra. You're doing a little bit of algebra to put this into a form that makes it more convenient when you actually want to go solve problems.